I'd like to do a sales pitch for our thermodynamic approach to economics, because many people have tried such things over the years, but we think we've succeeded at least in the context of what we call exchange economies. So this is joint work with Nick Chater, and simulations have been done for us by Yihang Luo that I'll show. So an exchange economy has a large, finite but fixed number of agents, and finite number of types of durable, infinitely divisible goods, one of which we call money, which have slight, has a desirability property. And in the economy, agents repeatedly exchange goods in encounters. So this is rather an artificial model, because you might say, well, once agents have got the bundle of goods that they want, why would they bother exchanging again? But, you know, maybe they've changed their mind one morning and would prefer something else. A basic economy, we mean one that has no barriers. So in this case, we assume convergence to a unique equilibrium. Equilibrium means a probability distribution, not an allocation. So it's a probability distribution, just like in statistical mechanics, given the total amounts of each type of good. Right? So the goods, the different types of good will spread themselves around among the agents with some probability distribution. But we'll be interested in what we call multi-part economies. So this is where goods of some types are constrained to certain subsets of agents, which we call components. So just think of an economy that has two islands, and maybe you can transfer some sort of good between the islands, but not other sorts of good. So for this, we assume convergence to a unique equilibrium, but now, given the total amounts of each type of good in each of its components. Right? So the good that can't transfer between the islands, we have to specify the amount of good on one island and the amount of good on the other island. And the question that we address is, what happens if one removes some barriers or puts two or more economies in some form of contact? So we could have two economies like the basic ones, and then allow contact between them. Okay, so our answer is that under some axioms, we use the axiomatic approach of Lieben-Ingwersen to physical thermodynamics. The important one I want to stress is extensivity. So we have to assume that for every economy and a scale factor, there's a scaled version of an economy that's possible. Then we deduce, using Lieben-Ingwersen, that each economy has a concave C2 entropy function S of its state. So the states here I'm representing rather schematically M and G. So M is the amount of money, G is the amount of good, which in general would be a vector for different types of good. And if there are constraints on where between which parts of the economy money or goods can flow, then of course these need to be vectors that indicate the amounts in each component. But anyway, there is an entropy function, and the principal property is that if you put economies in contact, total entropy cannot decrease. So it's just like in physics. On the other hand, it's different from usually economists' view. Economists might say, well, an economy has some utility function, and but each economy would not want to reduce its utility. And the outcome would be Nash. Whereas in our theory, it's possible that there could be a decrease in entropy in one island, say, compensated by a bigger increase in the other island, and that will be permissible and achievable. So that's the short version of the answer, but we have a lot more consequences that come from this. So firstly, each economy has a financial temperature, which is just 1 over ds by dm. And if you put two economies into financial contact, so allowing flow of money but not other things, then money flows from hotter to cooler. And, the question of international money flow, for example, is an enormous one that I've read things by people in the Bank of England about, and they basically don't have a good theory of it. So anyway, we have this concept of temperature, which explains which way money flows. And secondly, each good, say type I, has a marginal value, nu I, which is just ds by dgi. And the economy, if you put it in contact with what we call an external trader, who offers to buy or sell at a price, then the economy buys from or sells to the trader, according as the trader's price is below or above what we call the market price, mu I, which is just temperature times this value, nu I. Okay, so we can say which way trade's going to go. One can make money out of temperature differences, just like a Carnot cycle. And indeed, the amount of money you can make, the maximum amount you can make, compared to the money, say, transferred from the hot economy, is given by the usual Carnot efficiency factor. We deduce that there are what in physics would be called Maxwell relations, and economics for individual agents are called Hotelling relations between partial derivatives. So think of things like the derivative of the value of the ith good with respect to the amount of the jth good. And because mu I was defined already as a derivative of the entropy, then this is actually a second derivative, so it's symmetric. But we get stronger things from the concavity of entropy, namely non-negativity of various matrices of partial derivatives, including the diagonal elements. And the last one that I'm mentioning here is we deduce inequalities between derivatives of quantities subject to constant amounts versus constant prices. So this is something that economists do at the level of individual agents or companies. I'm not going to go into that more, but this concept called compensated derivative, where when you change goods, then you have to change the money at the price, market price, in order to buy the goods or sell the goods. Okay, so that's a list of consequences. I'm going to illustrate them by simulations that Yang Luo did. And the simplest example that he studied is what we call Cobb-Douglas economies. Each agent has a utility function, in quotes, because it's not used in the standard way that economists use utility functions. But U for the amount of money, let's just suppose there's money and want or sort of good. It's obvious how to generalize. U, the utility for this agent to have M of money and G of good, is M to some power and G to another power. That's why we call it Cobb-Douglas, because they often consider things like this and call after Cobb and Douglas. And on pairwise encounter, agents pool their belongings and redistribute them between themselves with probability density proportional to the product of the utility functions. So this is how we use utility. So it means there's a bias towards higher utility, but it's probably stochastic. So it doesn't actually mean that each agent increases their utility. So I said that on putting two economies into financial contact, money will flow from hotter to cooler. And that's what we illustrate here. We put two of these Cobb-Douglas economies into contact. One starts at a hotter temperature, 100, and the other at 50. We let them settle down, and at time 0.01, we put them in financial contact, and we see the temperatures converge together. And you can plot the money flows, and indeed the money is going from hotter to cooler. And they settle down. Of course, there are fluctuations. That's because our economies are finite size, I can't remember how many agents there were in this, but 100 or 200, something like that for each economy. And actually, if we take a statistical mechanics view, then we can interpret the size of the fluctuations using Einstein fluctuation formula, and it fits. The second picture here shows a contact with an external trader offering a given price. So the blue curve, we start with the amount of goods in the economy being 500,000. And at this time, we put the economy in contact with the trader, say the blue curve offering a price 0.9. So the market price actually start with as 1. One can compute everything explicitly actually for these Cobb-Douglas economies. And what we see is that the amount of goods, traders offering 0.9, so that's a bargain for the economy, so it buys goods. The amount of goods in the economy goes up to 530,000 or so, and then settles down, fluctuates around there. And indeed, we can predict what price it should settle down to modulo fluctuations, and it's 527,777. And the other curves are for prices 0.95, price of 1, where there's no net change, and then a price 1.05, 1.1. Okay, so the goods flow the direction that we said. Next, we think about putting two Cobb-Douglas economies in full contact. So we allow a flow of money and goods. And our initial condition in this picture is over here. The contours are contours of constant total entropy. So maximum entropy points in the middle, we start somewhere here. And the coordinates I'm using are the goods and the money in one of the two economies, say economy 1. And because money and goods are conserved, we've just put them in contact, then you can easily deduce money and goods in the other one. And what you see is we did several simulations. Then the path goes from the initial condition and then hovers around the maximum entropy point. Here's another simulation with a different initial condition. Again, it goes to the maximum entropy point. But what I've done to compare with standard economics is to draw curves where we have constant entropy of the second economy, that's this blue curve, and constant entropy of the first economy, the orange curve. And standard economics, if each economy would refuse to decrease their entropy, would mean we'd be constrained to this region between the two curves. So this is called Edgeworth box analysis for those who've seen that. So that indeed fits for this initial condition, but not for this one. See here, putting the economies in contact actually moves outside the zone between the two Edgeworth box curves. So this produces a difference with standard theory. Okay, next I wanted to illustrate Carnot cycle. We suppose we have an external trader who trades with what we call a ship economy, and the trader puts the ship into alternate financial contact with hot and cold mainlands. So let's start here. This is temperature and total goods on the ship. So the ship was starting at the temperature of the cold economy, 20. And the trader buys goods from the ship. So the amount of goods decreases. Temperature goes up on the ship because the amount of money goes up on the ship. And then the trader puts the ship in contact with the hot mainland when the temperature on the ship reaches the temperature of the hot mainland, which is 26. Then the trader sells goods to the ship, but keeping it in financial contact with the hot economy. So the temperature remains, apart from fluctuations, at 26, the amount of goods increases. Then at this point, the trader disconnects the financial contact with the hot mainland, but carries on selling goods to the ship. And we go down here until we reach the temperature of the cold economy, at which point the trader puts the ship in contact, financial contact with the cold, and buys goods from the ship, and we go around here. And in this process, money leaves the hot economy, some of it arrives at the cold economy, and the trader pockets the rest. So this is how to make money out of temperature differences. In reality, the hot and cold mainlands are not infinitely large. So here we plot a simulation where we take finite size, and we get some decreasing spiral. So you can still, the trader still makes some amount of money. Okay, I see I'm running into question time, so I'll try and speed up to finish. So partial derivatives, to make it interesting, we considered what we call a substitutes economy, whose agents don't notice the difference between two types of goods, G and H. They're equivalent, so in their utility, it's only the sum that matters. And another sort of economy, complements economy, where two types of good are only useful if you've got the same amount of the other. So the minimum of G and H is what's important. And then we measured this partial derivative of value with respect to amount of goods for a substitutes economy on the left and for a complements economy on the right. Okay, so what we see is fairly good symmetry in both cases. And we see negative definiteness because the diagonal elements are negative everywhere, and the determinants are positive, which are 2 by 2 determinants. Yep.
Yeah, you have around 3 minutes to conclude.
Yep. So this confirms symmetry, negative definiteness. Another thing we've done is on Saga matrix. If you put two economies in contact, then if you have a value difference, you should get a flow. And actually, it was more convenient to do the opposite way around. We force the flow and see what value difference we get. So we're estimating the inverse on Saga matrix. And the theory says this should be positive definite. And indeed, that's what we get. Here we've got money and two types of good. And you see that we get positive definiteness. One can include behavioral effects. So one type of model that we call the Bouchot economy, because it was stimulated by a paper by Bouchot et al. Here we just have only money, actually. The utility of the ith agent for a vector of money now depends not just only on its own money, but the mean money squared, actually, in the whole economy. So this has a herding effect. And we checked that if we put two Bouchot economies in financial contact, we still get the same thing. We get money flow from hotter to cooler economy, and they settle down to a common temperature. The last thing that we've been doing is calorimetry. So suppose you have complicated economy, still in silico, but in principle, we'd like to do this in reality. Then you could, in principle, measure the entropy function by integrating ds is beta dm plus nu dg. And so Yuhang did that, and for an example, and gets a surface like this. So indeed, we get something concave C2. And the main point is that this integration is indeed path-independent modulo fluctuation errors. So to conclude, we presented a theory. There are two papers. One is in arXiv, and the simulation one has already been published. We're interested in extending to include realistic things like manufacturing, production, consumption, migration, multiple currencies. And what we'd like to do is to generalize to non-extensive economies and to non-equilibrium economies. Okay, so that's it.